Good morning, everyone. Today we are going to talk about characteristics, applications, and processing of polymers. The objective for today's class is we want to learn mechanical behavior of polymers. Uh, so look at this figure. It shows the mechanical properties of polymers, the stress strain curve behavior. So here it is a strain. This abscissor is a strain and alternate is a stress. And for different materials, we have different stress strain curves. And here, this one is an elastomer. So this one is a plastic. And so this one is a brittle material, brittle polymer. And brittle polymer means that it does not experience any plastic deformation before it fails, before it fractures, and which is totally different from this curve. And in this curve, it shows it has plastic deformation. And fracture strength of polymers is about 10% of those for metals. And we know this one based on our daily experience. And deformation strength for polymers, this is far bigger, much bigger than that of metals. It's about can be greater than 1000%. That means 10 times. For most metals, deformation strength is less than 10%. Then we talk about mechanisms of deformation, brittle, cross-linked, and network polymers. So this is the initial cross-linked, allied cross-linked polymer. So at the very beginning, and this is initial. So here is a near failure. You can go here. This is a brittle failure, and it is failure. You can see clearly, and so here and here, and detachment occurs. And for this is network polymer, it shows this one. Okay, this initial, and then so near failure, right? So also near failure, brittle failure, and here is you can see, and it is start fracture now. And then we talk about semi-crystalline polymer. This is the semi-crystalline polymer. So this is a brittle, still the brittle failure, and here is the plastic failure. So here is undeformed semi-crystalline structure. Semi-crystalline means that some part they are crystalline, some part are is amorphous. Amorphous is opposite to crystalline. So here, is if you apply the load further, and at this point, amorphous regions will elongate. Amorphous regions. You can see this part. And then further, the crystalline regions align. You can see, we can see the difference between this and this. Crystalline region align, and crystalline block segments separate. You can see clearly. Right? So this is a block segments separate. Look at as this one shows the bricks. And so here is a fibrillar structure. You can see the bricks. This is near failure. And then we talk about pre-deformation by joining. Joining, for example, monofilament, the fish line, and it stretches the polymer prior to use joining, and aligns chains in the stretching direction. Results of joining include increasing the elastic modulus in the stretched direction, increase the tensile strength in the stretching direction, and decreases the ductility, the percentage of elongation. And annealing of the joining, we'll have learned this annealing when we talk about heat treatment techniques for metal and metal alloys. We talk about annealing. And here is also we can anneal these polymer materials. Annealing after joining can decrease chain alignment, reverses effects of joining, reduces Young's modulus and tensile strength, and we can enhance this percentage of elongation. And central, the contrast to the effects of cold working in metals. So be very, very careful. And then we talk about mechanisms of deformation for elastomers. Um, we still have brittle failure, plastic failure, and elastomer. And we can see, we compare elastic behavior of elastomers with the brittle behavior and this plastic behavior. So brittle behavior of aligned, cross-linked, and network polymers, and these materials failure mechanisms, and we just talk about them. And the plastic behavior, so we have semi-crystalline polymers as shown on previous slides. So this is the elastomer. You can this elastomer initial amorphous chains are kinked and cross-linked. So here is a deformation. This is elastomer. Deformation is reversible, elastic, and go up and go down. And you can tell this is the two parts are coincident. So they go up and go down. So here, final chains are straighter and still cross-linked and straighter. You can see we can compare, if we compare this figure with this figure, we can see this one, the chains are straighter, but still cross-linked. And then we talk about thermoplastics and versus the thermosets. So what is the thermoplastics? The thermoplastics they have the following characteristics: little cross-linking, and because little cross-linking, and we have is more ductile, soften with heating. When we heat it, it soften. And for example, polyethylene, polypropylene, and polycarbonate and polystyrene. So these are the typical thermoplastics. And what is the thermosets? On the contrary, the thermosets, they have the very, very different characteristics from those of these thermoplastics. For thermosets, they significantly cross-linked on 10% or to 50% of repeat units, are hard and brittle, and do not soften and will be heated. And vulcanized rubber, epoxy, polyester resin, and phenolic resin. So these are thermosets. So here is a molecular weight. So this is the molecular weight. So Tg is the glass temperature, and Tm is melting temperature. And so here is a mobile. This is a temperature. This is a molecular weight. So this is a mobile liquid, viscous liquid, rubber. So this is a top plastic. So this is a crystalline solid, and this is partially crystalline solid. So this figure shows us if we know how the molecular weight is related to the temperature, and the temperature determines the physical properties. So molecular weight along with the temperature, these two factors determine the final behavior, the material behavior. And then we talk about the influence of temperature and the strain rate on thermoplastics. And we talk about the thermoplastics and also thermosets. And sometimes we can be confused, especially for the beginners who just learned this one. And thermoplastics, you can just remember plastics. Plastics means that when we heat it, it will deform, it will soften. They will soften. So this is thermoplastic. Thermosets have the opposite material properties. This is the way I memorize the difference between these two very important groups of materials when I was a student, and you can use this technique also. Um, if we decrease temperature, and we can increase the Young's modulus, increase the tensile strength, and we will decrease the percentage of elongation, which is an indicator of ductility. And we have learned that the strength and ductility, and they are two competing properties. One is high, another must be lower, must be low. And you cannot possess, you cannot have a material that possesses both the high strength and high ductility. So if we increasing the strain rate, and we can increase the same effects as decreasing the temperature. So this figure shows and plots for semicrystalline PMMA there's the material behavior. So this is the material, this is the strain rate. I'm sorry, this is a strain, and so this is the different temperature, 4 degrees C to 60 degrees C. You can see if we increase the temperature, the Young's modulus becomes lower, tensile strength becomes lower, and it becomes more ductile. It is opposite to decreasing temperature. The melting and glass transition temperatures. What factors affects melting temperature and the TG glass transition temperature? And both these glass transition temperature, and so this is the melting temperature. Both Tm and Tg increase with increasing chain stiffness. Chain stiffness increased by presence of bulky side grooves, polar groups or side grooves, chain double bonds, and aromatic the chain groups. And so aromatic chain groups, this is a special chain groups. Regularity of repeat unit arrangements affects this melting temperature only. So this is glass, this is semi-crystalline solid, and so this is crystalline solid. So this crystalline solid behaves this way. The time-dependent deformation, right? So stress relaxation test, time-dependent deformation. A strain in tension to epsilon 0 and hold. And we can observe decrease in stress with time. So this is called stress relaxation test. Right? So this is a strain in response to epsilon 0. Observe the decrease in stress with time. So this relaxation modulus is calculated using this equation, sigma t and this epsilon 0. This is a function of time. So there is a large decrease in this ER, Young's modulus. So this is ER, okay, relaxation ER for T that for the temperature that is greater than glass transition temperature. You can see this is a TG. So this ER, so rigid solid transition region. So this viscous liquid, large relax. Representative, the TG values, and for different the polymers, we can have, and this is the different representative glass transition values, degree C. And then we talk about creasing during fracture of thermoplastic polymers. What is a crease? Crease formation prior to cracking. Right. So here is the body, and we can have fibrillar bridges here. So these are micro voids, and during creasing, plastic deformation of spherulites. What's a spherulites, guys? Spherulites is just like spheres, and formation of micro voids and fibrillar the bridges, microvoids and fibrillar bridges. So this one. And so this is the crack, right? When this is microvoids and come together, and we have this crack, have a bigger crack.